A simple experiment reveals something surprising. Heat a meal in the microwave and the food gets hot, but the dish often remains cold. This contradiction defies our intuition, but hides fascinating scientific principles. Today we'll explore what really happens inside your microwave and why some materials heat up while others remain unchanged. The first thing we need to understand is that microwaves are not ordinary heat. They are electromagnetic waves, like visible light or radio waves, but with a specific wavelength that interacts uniquely with certain molecules. Specifically, microwaves used in home ovens have a frequency of 2.45 gigahertz, carefully chosen to agitate water molecules. When we turn on a microwave, it generates these waves through a component called a magnetron. These waves spread throughout the oven cavity and begin to interact with the food. What happens next is truly amazing when observed at the molecular level. Water molecules, when exposed to microwaves, try to align with the oscillating electromagnetic field. As the field changes direction approximately 2.45 billion times per second, water molecules are forced to rotate frantically. This constant movement generates friction between the molecules, and this molecular friction produces heat. The more water present in the food, the more efficient the heating will be. That's why foods with high water content, such as soups or vegetables, heat up much more quickly than dry foods. But this still doesn't completely explain why your dish remains cold. To understand this, we need to examine what dishes are made of. Most microwave dishes are made of ceramic, glass, or certain specific plastics. The crucial factor here is that these materials contain few or no free water molecules, and more importantly, do not have charged particles that can move freely when exposed to microwaves. In simple terms, the materials of a microwave dish are structurally different from food. They don't have enough polar molecules that can be agitated by microwaves. Without this molecular agitation, there is no friction, and without friction, there is no heat generation. However, few people know that when your dish eventually heats up in the microwave, it is usually not from direct absorption of microwaves. Instead, the heat is transferred from the hot food to the dish through conventional thermal conduction. That's why the part of the dish in contact with the food gets hot, while the edges often remain cold. But not all dishes remain cold in the microwave. Certain materials react completely differently when exposed to microwaves. And this leads us to an intriguing question. Why are some dishes microwave safe and others are not? To answer this question, let's analyze the different types of materials and how they interact with microwaves. Number 1. Metals. Metals should not go in the microwave, but the reason is more interesting than you imagine. Metals have free electrons that can easily move through the material. When microwaves hit a metal, they cause these electrons to move rapidly, creating electrical currents on the metal surface. These currents can build up and generate sparks, especially on sharp or thin edges. Additionally, metals reflect microwaves instead of allowing them to pass through, which can create hot spots in the food or even damage the oven's magnetron. Number 2. Ceramics with metallic decorations. Many decorative dishes have finishes with gold, silver, or other metals. Even in small quantities, these metallic elements can cause electrical arcs inside the microwave. This explains why that beautiful cup with a gold rim should not go in the microwave. Number 3. Common glass and ceramics. These materials are generally safe because they are composed mainly of silicates, which have a rigid molecular structure without many free polar molecules to rotate. Microwaves pass through these materials without causing much heating. However, not all glasses are equal. Glasses that contain impurities or metallic components can heat unexpectedly. Number 4. Specific microwave-safe plastics. These are designed to remain stable under microwave radiation. They do not contain molecules that can be easily excited by microwaves and generally have low thermal conductivity, which means they remain relatively cold even when the food heats up. A surprising fact is that pure water in a perfectly smooth container can be superheated in the microwave, reaching temperatures above the boiling point without actually boiling. This occurs because the formation of bubbles necessary for boiling requires small imperfections on the container surface or impurities in the water. Superheated water is extremely dangerous, as it can boil explosively when disturbed. Now let's consider what happens when different types of foods are heated in the microwave. The heating efficiency varies drastically depending on the food's composition. Foods with high water content, such as fruits, vegetables, and soups, heat quickly and evenly. This is because water molecules are distributed throughout the food, allowing for more consistent heating. In contrast, foods rich in fats and sugars heat differently. Both fats and sugars are polar molecules that interact with microwaves, but not as efficiently as water. This explains why chocolate melts unevenly in the microwave and can frequently burn. Dense foods with low water content, such as breads and meats, can heat unevenly because microwaves penetrate only a few inches into the surface. The heat needs to propagate to the center through thermal conduction, resulting in hot edges and cold centers. Let's now look more deeply at the technology behind modern microwaves and how they were developed to overcome these limitations. The first microwave was accidentally created in 1945 by engineer Percy Spencer, who was working with radars at Raytheon. Spencer noticed that a chocolate bar in his pocket melted when he was near an active magnetron. Intrigued, he began experimenting with other foods, including popcorn, which popped as expected. This moment of serendipity led to the development of the first commercial microwave oven, launched in 1947. The first microwaves were huge, expensive, and primarily intended for commercial use. The first household model only appeared in 1967 and took another decade to become common in homes around the world. Modern microwaves incorporate several technological improvements to overcome the initial limitations. One of the main innovations was the addition of turntables. These plates ensure that foods pass through different points of the microwave field, resulting in more uniform heating. Another important innovation was the introduction of diffusers, which help distribute microwaves more evenly within the oven cavity. This reduces the occurrence of cold and hot spots in food. More advanced microwave ovens also include moisture and temperature sensors that can automatically adjust the power and cooking time based on the type of food. Some premium models even combine microwaves with other heating methods, such as convection or grill, to achieve results more similar to traditional cooking methods. Few people know that the 2.45 gigahertz frequency used in household microwaves was not chosen for being the most efficient for heating food. In fact, it was selected primarily to avoid interference with telecommunication frequencies. There are frequencies that could heat food even more efficiently, but they are reserved for communications. Now that we understand why dishes generally remain cold, let's explore some interesting exceptions and situations where this doesn't occur. Ceramic dishes with high iron content or other minerals can heat up in the microwave. These minerals can interact with microwaves in a similar way to water, generating heat. If a dish gets exceptionally hot in the microwave, even without food, it probably contains these minerals and should be replaced with a more suitable one. Old or colored glass containers may contain small amounts of lead or other metals in their composition, causing them to heat unexpectedly. Many colored glasses manufactured before the 1990s contain heavy metals that can interact with microwaves. Some plastics not designed for microwave use can heat up or even melt because they contain plasticizers or other additives that absorb microwaves. Besides the risk of melting, these plastics can release potentially harmful chemical substances into the food. Containers with trapped air bubbles, such as poorly vitrified porous ceramics, can heat quickly because the moisture trapped in these spaces absorbs microwaves. This can cause the steam to expand within the material, potentially leading to the container breaking. A curious phenomenon occurs with some types of fine porcelain. They can become extremely hot in the microwave due to microscopic impurities in the clay. These impurities create small hot spots that can propagate through the material. An interesting experiment you can do at home is to test the distribution of the microwave field in your oven. Place a paper towel covering the turntable and spread small pieces of chocolate evenly over it. Heat for approximately 20 seconds and observe the melting pattern. The areas where the chocolate completely melted represent hot spots, while areas with intact chocolate are cold spots. The understanding of these principles has applications beyond the kitchen. The same microwave technology is used in various scientific and industrial fields. In medicine, microwaves are used in physiotherapy treatments to heat deep tissues without excessively heating the skin. Medical microwave diathermy equipment applies the same principle of selective heating to treat muscle injuries and joints. In industry, microwaves are employed to dry wood, ceramics, and other materials more quickly and evenly than traditional methods. Selective heating allows moisture to be removed without damaging the material. Chemical laboratories use microwave digesters to prepare samples, accelerating reactions that would normally take hours to occur. This method is particularly useful in environmental analyses and forensic studies. In the food industry, microwave pasteurization and sterilization processes are being developed as more efficient alternatives to traditional methods. These processes can better preserve the flavor and nutrients of foods. Even in agriculture, microwaves are experimentally used for pest control and grain drying, offering potentially more ecological alternatives to conventional chemicals. Microwave heating technology continues to evolve. Researchers are developing variable frequency microwaves that can automatically adjust for different types of food. Imagine a microwave that detects whether you're heating a soup, a piece of meat, or a plate of vegetables, and adjusts its frequency to provide the optimal heating for each type of food. Another promising advance is the development of real-time imaging systems that can monitor the internal temperature of foods as they are heated. This would allow the microwave to dynamically adjust its power to ensure uniform heating, eliminating the problem of super hot edges and cold centers. 3D printing is being explored to create containers with specific thermal properties that could heat in a controlled manner in the microwave. These smart containers could, for example, remain cold in handling areas while efficiently transferring heat to the food. Now you understand the fascinating physics behind this everyday phenomenon. Microwaves heat your food by agitating water molecules, while most dishes remain cold because they don't have these free polar molecules to interact with the radiation. The next time you heat something in the microwave, observe how different materials respond in distinct ways. This simple observation connects you to fundamental principles of physics that scientists continue to explore and apply in new fields. If you like this explanation about microwaves, leave your like and tell us in the comments what other engineering or technology phenomenon you would like us to explain. Subscribe to the channel for more content that reveals the science behind everyday life. Until the next video.